hopefully you recognize that as a percent sign. It just means per 100. In other words, you take something and you put it into a form that gives you amount per 100. And percent yield is something chemists and chemical engineers, people that work at the refinery or other places that make chemicals, they're very interested in percent yield. And percent yield is easy to calculate. It is just the actual yield. Now, that's what you get in the manufacturing process or maybe in a lab that you are doing. So, this number that you get right here is often has to be given in a problem because you can't get it unless you're doing a manufacturing process. You can't get it unless you're doing a lab. So this number will have to be given to you in the problem for your chemistry test or chemistry worksheet. Actual yield has to be given. Like, it's not something that you can calculate. Actual yield has to be given. It is the actual yield divided by theoretical yield. And in order to be a percentage, then you have to multiply that fraction by 100. That's what makes it a percentage, is when you multiply by 100. By the way, if you were calculating parts per thousand instead of parts per hundred, what would you multiply by? 1,000. What if you were doing parts per million? Yeah. What if you were doing parts per billion? It's the same, it's the whole same idea. It's just for parts per billion. Usually they're talking about a much smaller number. Okay, so that is percent yield. Now for chemistry problems, this theoretical yield right here is calculated using stoichiometry. So that's why we are putting it here in this stoichiometry unit. Often you would just be doing this. You'd have a lab and you'd say, how much did you make? And you got this much, and you should have made this much, and you'd calculate percent yield. Or you'd do the same thing if you were manufacturing something like diesel fuel out of crude oil coming in to the plant up in Anacortes. That would be where you might expect to see someone calculating experimental yield. So if someone said, I need you to describe how to determine the percent yield of a chemical reaction, let me just type that. Can you read this? Come on, put on your glasses. Can't you guys read that? Okay, is that big enough to read, or do you want it bigger? We can go a little bigger. Let's go to something like 72. Woo, we can read that. Describe in words how to determine the percent yield of a chemical reaction. That's the next thing I'm going to put into your notes here. Describe in words how to determine the percent yield of a chemical reaction. Well, here is what I would say would answer that. The first thing you have to do is you have to calculate your theoretical yield. you have to calculate your theoretical yield. Then you have to use some kind of experimental or actual yield and the reason we kind of have two terms here is experimental might be in some kind of laboratory setting. Actual yield might be a term you might use if you're working at a manufacturing facility, but either one of these would work. You use the experimental or actual yield from the problem and here we're kind of assuming that this is written out for you. And you substitute that into the formula to calculate the percent yield. It's really quite simple. And the reason we're not spending huge amounts of time practicing this, we're starting the review process for the test tomorrow. We're not spending a lot of time practicing this is because you are used to doing this on a regular basis, right? Because what's the percent yield on your test if you got 25 out of 50? What's your percent yield? 50%. It is that same formula that you're used to using to calculate your score on something. It's just this right here. Actual divided by what you could have gotten, what you should have gotten, and that thing you should have gotten came from stoichiometry. So I want to set up a problem now so that you get a chance to practice this. And I'm going to set this up with this chemical reaction. Potassium hydroxide yields potassium oxide plus water. So if you take potassium hydroxide and you make it decompose, and we're going to tell you that you're going to start with 1.52 grams of potassium hydroxide. We're going to put our experimental yield of potassium oxide is 1.10. So we did an experiment and we made 1.10 grams of this. How do we find our percent yield? Well, the first thing we're going to do is we're going to calculate our theoretical yield. And to do that, we have to balance the chemical equation. So we're going to go through the steps to do a stoichiometry problem here, right? So to do the stoichiometry problem, we need to answer this question. How much potassium oxide would we expect to make? And that number is going to be our theoretical yield. And that we have to calculate using stoichiometry. So the first thing we have to do is balance the chemical equation. So to balance that, I'm just going to start with potassium and go, oh, 1 potassium there, 2 here, so I need to add a coefficient. Now that may not be our final coefficient. We'll just have to see here. That gives me 2 hydrogens. Here I have 2 hydrogens. So far, so good. I usually leave oxygen to last, and here I see 2, and here I see 1, 2. So it is balanced with that coefficient of 2 in front of potassium hydroxide. So we need to find this number right here. How much would we expect to make? And we'll compare that to how much we actually made. So let's do that stoichiometry. I'm going to start with 1.52 grams of potassium hydroxide. I'm going to change that to moles. And I'm going to write in all the units before I do any more numbers because I think that's a useful way to approach stoichiometry problems. And I haven't modeled enough of these for you probably. We're going to change grams to moles, right? So I'm going to put moles on the top. That's moles of potassium hydroxide. Then in the next conversion factor, I want to convert from moles of potassium hydroxide to moles of the thing with the question mark under it. So this new unit right here should be moles of K2O, potassium oxide. And then I'm going to make the next unit, I'm going to force the next unit to be grams of K2O. Right? Because that's what I want to end with. Now, how do I force those units to occur? By making them cancel out one step at a time. So I'm going to make this unit cancel by writing the same unit down here, KOH. Now those units have canceled. I'm going to make this unit cancel by writing the same unit down here. I'm going to make, that way this unit cancels. I'm going to make this unit cancel by writing the same unit down here. And that's K2O. Take a moment. Do you have those units in the right places? Now we're going to take a few moments to come in here and put in numbers into our problem. Numbers in the correct places. So to make it easier for you to glance up and see where I'm putting in numbers, this number and this number are always going to be ones because we want the number of grams in 1 mole. So right here, this is going to be the molar mass of KOH. That's potassium, oxygen, hydrogen added together. There's 1 of each. You guys look along, be sure you're getting the same thing I'm getting to make sure I'm right, because you're checking my work. You're the only people here to check my work. So 39.1 is the molar mass of potassium. Oxygen is 16. Hydrogen is 1.01. So we should be able to simply add those together and get is it 56.11? So that's the number I'm going to put here. for the molar mass. 56.11. I'm going to do the molar mass now of K2O. That's 2 potassiums. Potassiums were 39.1. So 39.1 times 2 is 78.2. Did I do that right? Yeah, 78.2. Oxygen is 16. There's one of those, so that's 16 added on here. And that should come out to be 94.2. Is that what you guys got? So that number, of course, goes up here. 94.2. Now, don't forget these numbers here. These numbers here are from our balanced chemical equation. And in the top is going to go the 1 that is there. And on the bottom with KOH, it's going to be this 2. So let's put those in the right place. On the top, K2O, it's going to be a 1. And on the bottom is going to be a 2. That comes from up here and up here. So now we can calculate the answer. So 15.52 1.52 times 1 divided by 56.1 times 1 divided by 2 times 94.2 divided by 1 equals, did you guys get something really close to 1.28 grams of K2O? Now remember, this is the theoretical yield. That's why we were finding this, is because this is theoretical. That's what we would expect to do to get when we carried out this reaction. So now we have everything we need to calculate percent yield. Percent yield is the experimental yield of 1.10 grams. And you guys know where that came from, right? That number came from right up here. And we're going to divide that by 1.28. The units, of course, cancel out because percentage, weirdly enough, percentage, the units always cancel out. Of course, don't forget to multiply by 100. That's what makes it per 100. And remember where the 1.28 came from. the 1.28 came from right there. And you should have gotten something like 85.9%. So that's how you calculate percent yield.